Lab 4, Zephyr Smith. So the point of this lab is to not let me enjoy my spring break because I'm working on physics instead of spending time with my grandma. Also to use the loop rule and conservation of charge to predict the behavior of circuits and use meters to confirm these predictions. So for the model, I used this online tool, and I assumed that there was no resistance in the wires and the ammeters, and that the EMF is equal to the change in voltage due to all of the circuit elements working together. So the circuit components is the system, and the surroundings is everything else, including the beautiful day that I'm not getting to enjoy because I'm working on this physics lab on my spring break. So my predictions, I predicted that I would be constant throughout the whole thing, and that the resistance would be equal to the resistance of all the components. With there's two resistors, one is 47 and one is 100, so 147 ohms of resistance, and that the current would be 0.02 amps, which the actual reading was 0.02 amps. So I was right about that. And then once I attached the voltmeter, the amps dropped to 0, and the volts were at 3, and that's because it was an open circuit, so there's no current in there, but the voltage is still 3 because of all the components and stuff. Some more measurements. Once I made it closed circuits again, and then I measured all the way around the circuits. We got from B to A, which is the batteries, that's 3 volts, and then from D to C, that's minus 0.96 volts, and then F to E is minus 2.04 volts. And if you look at that, if you add up those two, it is equal to negative 3 volts, which means that the voltage from the battery minus the volt or plus the voltage of the resistors equals 0, which means that it follows all the laws that we learned. This was the graph that I drew. You can see for C to D, in both the spots where there's a resistor, the voltage goes down, which is because that's what a resistor does. And then, yeah, when it's in parallel, you can actually see that the current went up, and that's because there's less resistance, because some of the current does not have to go through the capacitor, which means it's more resistance, and you can see my calculations right there. And then I had a light bulb and a capacitor. And so when I started it with the battery and the capacitor, the light originally was lit, and then as the capacitor charged, the energy moved to the capacitor, and the light was not lit anymore. And then when I disconnected the battery, the energy discharged from the capacitor to the light bulb, so it did the same thing. It lit up and then faded, and you can see the times right there. And then I recorded some times into sheets and put it on a graph, or put the linearized version on a graph. And I can see that the slope was negative 0.167. And so when I did my calculations, it showed that the RC is equal to 5.99 seconds, which is very close to our expected RC, which makes sense because it's a perfect model. Yeah, as I said, the model is perfect. A source of error might be the stopwatch. Since I am a little bit slow, I'm a little bit mentally challenged. And I did use my phone stopwatch, so yeah, it could be that. What if I was doing this lab in real life using real ammeters? So real ammeters, they actually do have a small amount of resistance, so that would affect the measurements. And then what if I used a real battery to charge a capacitor with no resistor in the circuit? I think it might be dangerous, and I think that I might shock myself because I'm not very good at working with circuits. Okay, thank you.